There is a question that most of us were never supposed to ask. Not because it's forbidden, not because the answer is dangerous, but because for most of human history, the question itself was considered meaningless. A grammatical error dressed up as philosophy. Something serious people set down quickly and walked away from. The way you'd set down a cup with no bottom. The question is this: what was here before the beginning? Tonight, we're going to ask it anyway. And we're going to discover that the people who spent their entire careers telling us it couldn't be answered have spent the last several decades quietly, seriously, and sometimes furiously trying to answer it themselves. Get comfortable. Let your body settle. You don't need to hold on to every word. This is a long walk, and we're going to take it slowly, the way a question this old deserves to be taken. Here is what you were probably taught. Around 13.8 billion years ago, everything that exists erupted from a single, unimaginably hot, unimaginably dense point. Space itself expanded outward from that moment. Time itself switched on at that instant. Before it, there was nothing. Not darkness, not silence, not empty space waiting to be filled. Nothing. Not even the word nothing applies cleanly, because the word nothing still implies a somewhere. A container that happens to be empty. And there was no container. There was no somewhere. There was simply no before, because before is a word that needs time, and time had not yet begun. That is the story. It is clean. It fits on a single line, and it has one serious problem. The equation that produces it doesn't produce an answer at the very beginning. It produces something that physicists call a singularity, which is a polite name for a place where the math stops working, where the numbers don't go to zero, where they go to infinity. And infinity, in physics, is never an answer. It is what an equation prints out when you have pushed it past the edges of where it was ever designed to go. So the single most confident claim in the entire story, the claim that the beginning was the beginning, the absolute edge of everything, rests on an equation that falls apart at exactly that moment. A broken equation is not a description. It is a confession. It is the theory raising its hand and admitting it cannot tell you what is actually there. And here is the thing nobody says out loud in the textbooks. When that equation breaks, when the math dissolves into infinity and refuses to describe what it finds, the other laws of physics don't break with it. They keep running. They keep describing. They push backward right through the place where our best theory of gravity gave up, and they return, not silence, not nothing, but numbers. Finite, workable, strange numbers that describe real conditions, a real somewhere, a real something. 4 separate groups of serious physicists, working independently, using different mathematics, building on different foundations, pushed their equations past the wall. And all 4 of them found the same thing waiting on the other side. Not nothing, something, something ancient, something with structure, something with physics of its own that preceded every particle you are made of, every star you have ever looked at, every atom in the air, moving slowly through this room right now. Tonight, we are going to walk to that wall, and then we are going to walk through it. Hold on to nothing. Let everything go quiet. We're going in. Let's start by giving the standard story its full due. Because what we're about to question is not a careless guess. It is one of the most thoroughly tested, most precisely confirmed pictures of reality that science has ever produced. And it deserves a fair hearing before we start pulling at its edges. Here is what we actually know, and know well: the universe is expanding. Not in the sense that galaxies are moving outward through space like debris from an explosion, but in the deeper sense that space itself is stretching, carrying everything within it gradually further apart. We have measured this expansion with extraordinary precision. We can watch it happening in real time. In the light of distant galaxies, whose colors shift toward red, the way the sound of a passing train drops in pitch as it moves away. Run. That expansion backward, the way you would rewind a film, and everything that is now spread across hundreds of billions of light years rushes back together. Galaxies converge. Space shrinks, temperature climbs. Matter grows denser and denser as it is packed into a smaller and smaller volume. The film keeps rewinding, hotter and tighter. until we arrive at the conditions of the very early universe, a state of such fierce, concentrated energy that nothing we interact with in daily life would survive it for an instant. We know this picture works because it makes predictions, specific, checkable, falsifiable predictions. It tells us, for instance, exactly which light elements should have been forged in the first few minutes of that hot, dense state. How much hydrogen, how much helium, how much of the faint traces of lithium scattered through the oldest stars. We went and measured those proportions in the universe. They matched. Not approximately, precisely. To a degree that should give you a quiet, settled feeling that the story is correct, at least for everything from a few minutes after the beginning onward. It tells us that the universe, as it cooled from that early state, should have left behind a faint glow of radiation, stretched by billions of years of expansion into the microwave range, filling the sky equally from every direction we looked. It was there, exactly where it should be, exactly the temperature it should be, smooth and uniform to within 1 part in 100,000, an afterglow of the early universe. Still washing over the earth tonight, still passing through this room, and through you at this very moment. The model works. It works beautifully, in fact, for almost everything it touches. The confidence cosmologists speak with, when they describe the early universe, is not arrogance. It is confidence earned by decades of predictions made and then confirmed, one after another, by independent instruments built by independent teams on opposite sides of the world. But here is where the beauty of the story and the honesty of the story start to pull in slightly different directions. Everything the model describes with such precision, the light elements, the ancient glow, the expansion rate, all of it lies safely downstream from the very first instant. The model is describing what the universe was doing once it was already underway, running, cooling, expanding, settling into the structures we now see. So, the very first moment, the one the story begins with, the one everything is supposed to have erupted from, is a different matter entirely. That moment is not where the model succeeds. That moment is precisely where the model breaks. And there is a difference. An enormous and important difference, between a story that works for almost everything and a story that works for everything, including its own starting point. The most confident word in the entire account, the word beginning, is the one word the mathematics cannot actually support. Because at the beginning, the mathematics doesn't give you a picture. It gives you an infinity. And an infinity, as we are about to see, is not the universe telling you where it started. It is the theory telling you where it stopped being able to look. That is where we go next. Into the exact place the equation breaks, and what it means that it breaks there, and what the breaking is actually pointing at. The equation in question belongs to Albert Einstein, and before we talk about where it fails, it is worth saying clearly how extraordinary it is in every place it doesn't. General relativity, Einstein's description of gravity, is not a theory in the casual sense people sometimes use that word, as in a guess, an educated suspicion, something smart people believe until something better comes along. It is one of the most precisely tested frameworks in the history of science. It predicted that massive objects would bend the path of light passing near them. And when astronomers measured starlight curving around the sun during a solar eclipse in 1919, it bent by exactly the amount Einstein said it would. It predicted that two massive objects spiraling toward each other would send ripples through the fabric of space itself. And a century later, we built machines sensitive enough to feel those ripples arriving from 1 billion light-years away, carrying the exact signature the theory described, called the satellites, that tell your phone where you are on the surface of the Earth, have to correct their clocks using general relativity, because time runs at a slightly different rate in orbit than on the ground, exactly as the theory predicts. Ignore that correction, and your navigation drifts by miles within a single day when I tell you this theory breaks. I am not telling you it is unreliable. I am telling you that the most reliable theory we have ever built about space and time reaches a specific place, under specific conditions, and admits it cannot go further. That place is the singularity. Here is how you arrive at it. Take the expansion we described in the last stretch of our walk and run it backward. The universe contracts. Space shrinks. Temperature climbs. Density rises. The equations of general relativity follow this rewinding film with perfect composure for a very long way. They describe the conditions at 1 second after the beginning, at 1 millisecond. At 1 microsecond they keep going, the numbers growing more extreme with each step back but remaining numbers, finite, describable, workable. And then, at the very first instant, something changes. The equations reach a point where the density of everything that exists is asked to fit into a volume of zero size. And zero size is not a very small size. It is no size. It is not a container approaching its limit. It is the absence of a container altogether. And when you divide any quantity, however large, by zero, you do not get an answer. You get infinity. The theory, at that exact moment, stops returning numbers. It returns something that is not a measurement, not a description, not a fact about the universe. It returns a signal, and the signal is this: God was not built to describe what is here. There is a simple analogy that captures what is happening. Imagine you are calculating how the brightness of a lamp changes as you walk toward it. The mathematics of that calculation is straightforward, and it works perfectly for every distance greater than zero. But taken literally, the formula claims that at zero distance, the brightness becomes infinite. The lamp becomes infinitely bright, which is, plainly, nonsense. What is actually happening is that the formula, which was built to describe the behavior of light across open space, has been pushed into a regime it was never designed for. The infinity is not a fact about the lamp. It is a fact about the limits of the formula. The singularity at the beginning of the universe is the same kind of signal, green, written not across one calculation, but across the entire fabric of space at once. Einstein's theory was built to describe the behavior of space and time across the universe we can observe. It was not built to describe conditions at the extreme, where matter is packed into zero volume, and where quantum effects, the strange rules that govern the smallest scales of reality, become not negligible, but completely dominant. Roger Penrose and Stephen Hawking proved in the 1960s and 1970s that this breakdown is not a flaw you can engineer your way out of. Within the rules of general relativity, given the universe we actually observe, the singularity at the beginning is forced. It is built into the theory's own structure. The theory is telling you from the inside exactly where it runs out. And here is the crucial thing that the standard story quietly skips over. There is an enormous difference between saying our best theory cannot describe what came before, and saying therefore nothing came before. The first statement is honest. Says we have reached the limit of one particular tool. The second statement is a claim about reality itself. A claim that nothing exists on the other side of that limit, and that claim does not follow from the first. It never did. It was assumed quietly, almost invisibly, layered into the way the story got told, until it hardened from an assumption into a certainty that nobody remembered making. The equation doesn't say nothing was there. The equation says it cannot see from here. Those are not the same thing and everything else tonight rests on the difference between them. In 1965, two engineers at Bell Laboratories in New Jersey were trying to get rid of a noise they couldn't explain. Their names were Arno Penzias and Robert Wilson, and they had been given access to a large horn-shaped radio antenna originally built for satellite communication. They wanted to use it for careful astronomical measurements, but there was a problem. A faint, steady hiss was coming from everywhere at once. Not from one direction in the sky, not from their equipment, not from the city nearby, from everywhere, the same quiet signal in every direction, at every hour, in every season. No matter where they pointed the antenna, they checked their instrument. They inspected every component. They famously discovered that a pair of pigeons had nested inside the antenna and left a coating of what they diplomatically described as white dielectric material. They cleaned it out. The hiss remained. What they had stumbled into, without looking for it, was the oldest light in the universe. Not the oldest light that any telescope has yet managed to detect, the oldest light that any telescope ever could detect. A fundamental ceiling, built not into our instruments but into the universe itself. To understand why that ceiling exists, you need to picture the early universe not the way it usually appears in documentaries, as a fireball expanding through empty space, but as a fog, an extraordinarily hot, extraordinarily dense fog, in which the particles of ordinary matter were packed so tightly and moving so violently that atoms could not hold themselves together. Electrons, which normally orbit quietly around the centers of atoms, were instead torn free, roaming through a superheated soup of charged particles, and light cannot travel through a soup like that. A photon, a particle of light, would move a tiny distance before striking a free electron and being knocked sideways, then move again, then be knocked sideways again. The early universe glowed intensely, but it was opaque. You could not see through it any more than you could see through the inside of a star. Then, roughly 380,000 years after the beginning, something changed. The universe had expanded and cooled just enough that electrons could finally settle into stable orbits around atomic nuclei, forming the first neutral atoms. In the span of a cosmically brief moment, the free electrons that had been blocking every photon's path simply disappeared from the soup, and the light that had been trapped scattered, bouncing endlessly through that charged fog, was suddenly released, all at once in every direction, streaming freely across the universe for the first time. That ancient light has been traveling ever since. 13.8 billion years of uninterrupted flight, stretched by the universe's expansion from a fierce hot glow into the faint microwave hiss that Penzias and Wilson couldn't explain. It fills the entire sky tonight, fills this room. It is passing through you right now, so weakened by its long journey that it carries almost no energy, just information, just the imprint of that exact moment when the universe first became transparent. And here is the wall. That released light, the cosmic microwave background, is the oldest signal any instrument that detects light can ever reach. Not because our telescopes aren't powerful enough, not because we haven't built the right detector yet, but because, before that moment of release, before those 380,000 years, the universe was opaque. No light from that earlier era was ever able to leave. It was all scattered and absorbed before it could begin any journey toward us. The James Webb Space Telescope, one of the finest instruments humanity has ever placed in space, can look back to galaxies forming a few 100 million years after the beginning. It will never see the first 380,000 years. Neither will any telescope built on any principle of gathering light, because the light that would have told us about that era never escaped to be gathered. Every image you have ever seen of the Big Bang itself, the brilliant point expanding outward into everything, is a reconstruction, a drawing built from theory. The oldest actual photograph stops at 380,000 years and goes no further. We are not looking at the beginning. We are looking at a wall made of the last light that was ever able to escape. And for a long time, we thought that wall was the end of what we could ever know. But it turns out the wall only stops one kind of messenger. And the kind it doesn't stop is stranger, quieter, and in some ways far more powerful than light. That is where we go next. There is a messenger that the wall cannot stop. It doesn't travel as light. It doesn't move as a particle, the way a photon does, or as a wave of electromagnetic energy the way radio signals do. It travels as something more fundamental than either of those. It travels as a ripple in the fabric of space itself. We call it a gravitational wave, and the single most important thing about it, for our purposes tonight, is this: the fog that trapped all light in the early universe, the dense soup of charged particles that scattered every photon before it could travel any meaningful distance, is almost completely transparent to gravitational waves. They pass through it, the way a sound passes through a wall that stops all light. The wall exists. The sound doesn't care. Right now, gravitational waves are passing through the Earth, through this building, through you. They are arriving from distant corners of the universe, from black holes colliding hundreds of millions of light years away, from neutron stars spiraling together in the dark. And they are moving through everything in their path, without slowing, without scattering, without leaving any trace except the faintest possible stretching and squeezing of space itself, a distortion so small that the first detectors, sensitive enough to feel it, had to measure a change in distance smaller than 1,000th the width of a single proton. We built those detectors anyway. In September 2015, the LIGO Observatory in the United States felt a gravitational wave arrive from the merger of two black holes over 1 billion light years away. The signal lasted less than a second. The distortion it caused in the 4-kilometer arms of the detector was thousands of times smaller than an atomic nucleus. And yet the instruments caught it, confirmed it, and announced it to the world the following February. A century after Einstein's equations predicted that such ripples had to exist, we finally felt one arrive. But the gravitational waves from individual cosmic events, the black hole mergers, and neutron star collisions we've detected so far, are not what matters most for the question we are asking tonight. What matters is something different, something that should be everywhere at once, rather than arriving from a single direction. A background hum, filling all of space, produced not by any one event, but by the conditions of the very early universe itself. In the first fractions of a second after the beginning, whatever actually happened there, whether a bounce, whether a collision, whether an emergence from a previous cosmos, would have stirred space so violently that the ripples produced would still be crossing the universe today, stretched and weakened by billions of years of expansion, but still carrying the exact imprint of the physics that created them. Physics from before the oldest light, physics from behind the wall, where the cosmic microwave background shows us the universe at 380,000 years old, and no earlier. A primordial gravitational wave background, if we can ever detect it, would show us the universe at a fraction of a second old. It would carry information from the era the light wall permanently hides. It would be a signal in a different language, written not in photons but in the geometry of space, arriving from a time no telescope that gathers light can ever reach. This is not speculation about a distant future technology. It is the entire scientific motivation behind the next generation of observatories being built right now, which we will visit near the end of tonight's walk. For now, what matters is the shift in possibility it represents. We began this walk facing a wall that seemed to mark the absolute limit of what could ever be known about what came before. And we have now found two ways past it. The first is calculation, the quiet power of physical laws that keep running where our instruments fall silent. The second is this, a different kind of signal entirely. One the wall was never designed to stop. The sealed room has a door after all, and on the other side of it, 4 completely different groups of physicists have each found something waiting. The first of them found a bounce. Imagine pressing a spring down with your hand. You feel it resist. The harder you push, the harder it pushes back, and at some point, when the coils are touching and the metal itself has nowhere left to go, the spring simply will not compress any further. There is a floor, a physical limit below which it cannot be made any smaller, no matter how much force you apply. The first framework for what came before the Big Bang says that space itself has a floor like that, and when the universe tries to compress past it, it doesn't vanish into a point, it bounces. To understand how physicists arrived at this idea, you need to know about a quiet disagreement that has been sitting at the heart of physics for nearly a century. We have 2 theories of reality, and they are each extraordinarily successful in their own territory, and they do not get along. The first is general relativity, which we have already spent time with. It describes gravity. It describes the large-scale structure of space and time, and its central picture is of a smooth, continuous fabric that can bend and stretch and curve, but that has no smallest unit, no grain, no minimum size below which it cannot be divided further. In general relativity, space is infinitely smooth. You can always zoom in one more time. The second theory is quantum mechanics, which governs the behavior of the very small particles, atoms, the forces that hold them together, and its central picture is almost exactly the opposite. The quantum world is fundamentally grainy. Energy comes in discrete packets. Measurements have minimum uncertainties below, which nothing can be pinned down. The quantum world is not a smooth sheet. It is a texture, and that texture becomes important at small enough scales. Almost every situation in physics, these 2 theories operate in completely separate territories and never need to confront each other. General relativity handles galaxies and black holes and the large-scale shape of the universe. Quantum mechanics handles electrons and photons and the behavior of matter at the atomic scale. The fact that they contradict each other at their foundations almost never causes a practical problem, because the situations where both would be needed at once are almost never encountered. Almost never. The singularity at the beginning of the universe is one of those rare cases. At the singularity, the entire mass of the universe is packed into a space so small that quantum effects are not negligible. They are everything. You cannot use general relativity alone, because it breaks. But you cannot use quantum mechanics alone either, because quantum mechanics does not describe space and time themselves. You need both at once, and they disagree. One serious attempt to resolve that disagreement is called loop quantum gravity. Its central proposal is as simple to state as it is radical to accept. If quantum mechanics tells us that almost everything in nature comes in minimum discrete units, why should space be the exception? What if space itself is grainy? What if there is a smallest possible size of space, below which the very concept of distance stops having any meaning? In loop quantum gravity, space is not an infinitely smooth sheet. It is woven from tiny discrete units, like a fabric with a finest possible thread. That minimum unit is almost inconceivably small, around 10 to the power of negative 35 meters. To give you some sense of that scale, a single proton is already unimaginably small. Compared to that minimum unit of space, a proton is larger than the entire observable universe is compared to you. We are talking about a smallness that makes the atom look astronomical, but the crucial thing is not how small it is. The crucial thing is that it is not zero. In 2001, a physicist named Martin Bojewold took the equations of loop quantum gravity and did something that required a particular kind of scientific courage. He ran them backward into the early universe, straight into the region where general relativity collapses into infinities, to see what his framework would find there. What he found was not an infinity. As the universe contracted in his equations, growing hotter and denser with each step back, the compression kept building exactly as before, right up, until it reached that minimum grain size of space. And there, instead of continuing to zero and producing an infinity, the compression met the floor, woven into space itself. It could go no further. The mathematics did not break, it turned. The contraction became expansion. The inward rush became an outward rush. The universe didn't collapse to a point, it bounced. Let the meaning of that land slowly, because it changes the entire picture. In this framework, what we call the Big Bang, that initial moment of fierce outward expansion that the standard story treats as the absolute beginning of everything, was not a creation, it was a rebound. Before it, there was a universe, a previous cosmos contracting, falling inward for perhaps an immense span of time, growing hotter and denser. As it compressed toward the floor, it didn't know was waiting. And when it reached that floor, the fall reversed. The energy that had been driving the contraction became the energy driving our expansion. The death of one universe's collapse became the birth of another universe's growth. Our universe. This one. The one you are lying inside right now. Now the natural question is what that previous universe was like. Whether it was similar to ours. Whether it had stars and galaxies and structures we would recognize, or whether it was something stranger and less organized. The honest answer from the mathematics is that the violence of the bounce would have smoothed away most of the fine detail. Whatever particular arrangement of matter and energy the previous universe had built up over its lifetime would almost certainly have been erased in the crushing passage through the floor. The bounce does not preserve the furniture of what came before, but certain fundamental features, certain properties of the quantum state of space itself, might have carried through. Faint whispers of a previous existence, encoded not in the arrangement of matter, but in the deeper structure of space and time that our universe was born into. We do not yet know whether those whispers are large enough to measure, or whether they have faded beyond any instrument we could ever build to detect them. What we do know is that where general relativity handed us an infinity, a place where the theory gave up and returned a number that means nothing, quantum gravity hands us a number, an enormous number, a density so extreme it staggers the imagination. Something close to what physicists call the Planck density, a value with nearly 100 zeros after it when written in ordinary units. But a number finite, describable, a place you can stand in the mathematics and calculate from, rather than a place where calculation ends. A finite number is a completely different kind of thing from an infinity. An infinity is a wall. A finite number is a place. I will not oversell this to you, because that is not how we do things here. Gloop. Quantum gravity is one serious attempt at reconciling general relativity and quantum mechanics. But it is not the only one, and it has not been confirmed experimentally. The energies involved in the bounce are so far beyond anything achievable in any laboratory that a direct test is not on any near-term horizon. The bounce lives in the scientific literature, carefully built, reviewed by other physicists, neither proven nor refuted. But it replaced an infinity with a number, Claude, and in physics, that is not a small thing. That is the difference between a door that has been sealed forever and a door that might, with the right instruments, be opened. Something was here before us, not as a wish as a result, written in mathematics that did not break where the old mathematics did. And the next framework goes further. It doesn't just say something existed before. It says that something lived a full life, built its own stars and galaxies, grew old, and left behind physical evidence we can search for in data we already possess. That idea came from a man who won the Nobel Prize, and it is where we go next. The second framework begins not at the beginning, but at the end. And the man who built it is worth knowing before we follow his reasoning, because the reasoning is only as credible as the mind behind it. And the mind behind it is one of the most rigorous in modern physics. Roger Penrose won the Nobel Prize in Physics in 2020. He did not win it for the idea we are about to explore. He won it for the work we already touched on earlier in our walk, the mathematical proof that black holes are not a theoretical curiosity, but an unavoidable consequence of general relativity. This is not a man arriving from outside the field with a beautiful story, Claus. This is one of the people who built the mathematical foundations the field stands on. When he proposes something that sounds at first almost impossible, the correct response is to slow down and follow the argument, because his arguments have a long history of turning out to be exactly right. His idea is called conformal cyclic cosmology. Wise. The name is technical, but the reasoning underneath it is something you can follow without any mathematics at all. It begins with a question almost no one asks when they think about the Big Bang. It begins with the end. Think for a moment about how our universe is going to die. Right now, the universe is full of activity. Stars burning, galaxies turning, light pouring across billions of light years in every direction. But that is a phase, and phases pass. The stars will exhaust their fuel and go dark, one by one, over timescales so long they resist any intuitive grasp. Galaxies will drift apart as space keeps expanding, growing lonelier and colder and quieter over trillions of years. The great black holes that anchor the centers of galaxies will slowly swallow what remains of the matter around them. And then even those black holes, over spans of time that make the current age of the universe seem like a single breath, will slowly evaporate, bleeding their mass away as faint radiation in a process, first described by Stephen Hawking, growing smaller and dimmer and cooler until they too are gone. What is left at the absolute end of everything is a universe with almost nothing in it that has mass. No stars, no planets, no black holes, no atoms in any form we would recognize. Just radiation, the last thin ghost of light and heat, spreading thinner and thinner through an enormous dark, cold, still expanding space. The universe not exploded but exhausted. Not destroyed but simply finished. Stretched to nothing across an infinite dark. Sit with the timescales for a moment, because they are part of why this idea feels so strange and so calm at once. The last small stars will burn for hundreds of billions of years. The era when the great black holes finally finish evaporating lies so far in the future that the number of years required to describe it would fill this page with zeros and still not be enough. Against spans like that, the entire history of stars and planets and everything humanity has ever done is less than a flicker. Near the very start of the story, Penrose stood at the far end of all of it, in the cold and the quiet long after the last light of the last star, and noticed something in that final state, when all the mass has decayed away and only massless radiation remains. The universe quietly loses the ability to define two things it has always defined: size and time. Here is why. Mass is what lets you build a clock, because a clock needs something that changes in a regular periodic way, and you need mass for that. Mass is what lets you measure size, because to say something is large or small, you need a ruler, and rulers are made of matter. But in that final mass-free state, There are no clocks left to tick, and no rulers left to measure with. The very concepts of large and small, of a long time and a short time, stop having any operational meaning. There is nothing left that could tell the difference between one scale and another. Now follow the consequence. If size no longer has any meaning in that final state, then the difference between unimaginably large and unimaginably small simply dissolves. A universe that is cold and dark and infinite and empty, in which scale has lost all meaning, turns out to have the exact same underlying mathematical structure as a universe that is hot and dense and tiny, in which scale has not yet come to mean anything either. The cold empty end of one cosmos and the fierce blazing beginning of the next are, in the mathematics Penrose developed, not merely similar, they are the same. They can be identified with each other precisely, like two descriptions of the same object written in different languages that, when translated, turn out to be identical. The infinite frozen future of a dying universe becomes, by a change in how scale is measured, the fiery birth of a new one. One cosmos ends, another begins from its ending, and then that cosmos expands and cools and builds its stars and watches them die, and at its own infinite end, another new cosmos ignites from the ashes of its geometry. Penrose calls each such universe an eon, and the sequence of them, quan, and flowing into the next across these surfaces of transition, we mistake for absolute beginnings, stretches back without limit and forward without limit. We are not the first, we are not the last, we are one aeon in a sequence that has no beginning and no end. Before our Big Bang in this picture, there was an entire previous universe. Not a brief collapsing phase, not a momentary transition. A complete cosmos that lived through its own long history. It had its own stars, its own galaxies, its own black holes that formed and grew over billions of years, and then spent trillions more years slowly evaporating, its own final silence. And when that silence reached the mathematical point where scale lost all meaning, that infinite cold ending became our blazing beginning. We are made in part from the ashes of a universe that is already over. Penrose did something that separates a beautiful idea from a piece of science. He asked what a previous eon would have left behind. Whether there was anything that could cross the boundary between eons. Any physical trace of that earlier cosmos that would have survived the transition and printed itself into the oldest light of the next universe, our universe. And he found something. The black holes of the previous eon, as they slowly evaporated over their immense lifespans, would have released enormous bursts of energy. Those bursts, passing through the transition between eons, should have left faint circular marks in the oldest light of the universe that came after. Rings of slightly different temperature, arranged across the sky like ripples frozen on the surface of a pond. Fossils, if you like, of a universe that lived and died before ours was born. He pointed at a specific feature, in a specific place, in data we already possess, and then he told the world to go and look, so people looked. In 2010, Penrose and a physicist named Vahe Gurzadian announced that they had found them. Not a prediction still waiting to be tested, an actual signal, sitting in the oldest light in the universe, that they claimed was the physical fingerprint of a cosmos that existed before ours. They had gone into the maps of the cosmic microwave background, the detailed charts of that ancient wall of light, and reported finding circles, concentric rings, regions where the temperature of the background light varied less than it did in the surrounding sky. Quiet patches in a noisy field, smooth circles, inscribed across the oldest portrait we have of our own universe, with no obvious explanation, in the standard story for why they should be there. Their interpretation followed directly from the framework we just walked through. These rings, they said, were the marks left by the final deaths of enormous black holes in the previous eon, as those ancient black holes completed their long evaporation, releasing the last of their energy in concentrated bursts. The ripples from those events crossed the boundary between universes and printed themselves as faint, circular patterns into the light of the next cosmos, our cosmos. The concentric rings were not random noise. They were the last signals ever sent by a universe that no longer exists if they were right. Then, what Penzias and Wilson heard as a quiet hiss in a New Jersey antenna, what satellites have since mapped in extraordinary detail across the entire sky. contained hidden inside it the echo of events that happened before our universe was born. Not a metaphor, a measurable mark, a number you could extract from data and hold in your hands. You can imagine the weight of that claim. And the response from the rest of the field was not applause. It was fast, technical, and sharply critical. Within weeks, several independent research groups published their own analyses of the same data. Their conclusion was uniform. The rings, they argued, were not special. The problem was subtle but important. To say a pattern is surprising, you first have to compare it against what a random, patternless universe would produce by pure chance. Penrose and Gerzadian had made that comparison. But the critics said they had made it incorrectly. When researchers generated simulated skies using the standard model of cosmology, ordinary universes with no previous eon, no inherited signals, no fossils of any kind, those simulated skies produced the very same kinds of concentric rings, simply from random statistical fluctuations in the temperature of the background light. One team tested the data using 5 different statistical methods. None of them found that the real rings were any more remarkable than the rings chance alone would produce. The signal, they concluded, was not a fossil. It was the ordinary texture of randomness and the human tendency to find shapes in it. That sounds like the end, but Penrose did not concede. And his response is the part that keeps this from being a simple story of a claim made and refuted. He pushed back on the simulated skies the critics had used. Those comparison skies, he argued, were themselves built on a set of assumptions baked into the standard model. Assumptions about the statistical pattern of temperature fluctuations that the theory predicts. If your comparison universe already assumes the standard story is complete, then finding that the real data matches it doesn't prove very much. You have, in a quiet way, assumed your conclusion before beginning your test. The comparison was circular. This is not a rhetorical move. It is a recognized and genuinely difficult problem in this kind of work. One that has never been cleanly resolved. The argument evolved. By 2018, Penrose and a new set of collaborators had sharpened the search into something more specific. They were no longer looking for the broad concentric circles. They were looking for what they called Hawking points, named for the man whose work on black hole evaporation the prediction depended on. The idea was precise. The very last burst of energy from a dying black hole at the end of the previous eon. The final release as the hole evaporated completely should appear in our oldest light not as a ring, but as a small spot of slightly elevated temperature, surrounded by a faint warm halo, a point, not a circle, a different kind of fossil from the same event. They reported finding candidate points at a level of statistical confidence their team described as meaningful. Other researchers examined the same data and disagreed, concluding that the number and intensity of such spots did not exceed what a standard universe would produce by chance. A careful reanalysis published in 2024 found no statistically significant signal remaining once certain corrections were applied to the data. So where does that leave us? It leaves us with a question that is genuinely open, neither confirmed nor cleanly buried. The honest weight of evidence currently leans against the claimed signal. Most cosmologists do not believe the fossils have been found. That is the real state of play, and dressing it up would not serve you. But here is the part worth sitting with. Regardless of how the statistics eventually settle, a Nobel laureate took an idea about a universe that existed before our own, and instead of leaving it as philosophy, he derived from it a specific, concrete, testable prediction. He said, the previous cosmos should have left a particular kind of mark, of a particular shape, in a particular place, in data we already hold in our instruments. Then he went and looked. Then other researchers checked his work, challenged his methods, tried to break his analysis using their own tools. That argument, that back and forth over null comparisons and statistical thresholds, and the assumptions hidden inside simulated skies, is not the system failing. It is the system working exactly as it should. The question of what came before our universe became a question with a prediction attached, a prediction that could be tested, argued over, and potentially proven wrong. Whatever the fossils ultimately turn out to be, the fact that fossils of a previous universe are the kind of thing that can be searched for at all, in light that is passing through this room tonight, is something the old story of absolute beginning could never have offered. You cannot search for the remains of something the story says never existed. Third framework doesn't put a single universe before ours. It puts an infinite number of them. And it arrives not from a new theory invented to answer the question of what came before, but as an almost unavoidable consequence of a theory built to answer a completely different question entirely. A theory that was designed to explain a stubborn puzzle in the oldest light, and that solved it so cleanly, so completely, that the side effect it produced was almost too strange to accept. The puzzle is this: when we look at the cosmic microwave background, the ancient light we spent time with earlier, we find that its temperature is the same in every direction, to within 1 part in 100,000, not roughly the same, extraordinarily, almost impossibly the same. The light coming from one edge of the observable universe matches the light coming from the opposite edge to a precision that should take your breath away. That sounds like a fine thing, a tidy universe, until you realize what it requires. The two opposite edges of the sky we are looking at are so far apart that in the standard story, light could never have traveled between them in the entire age of the universe. They have never been in contact. They have never exchanged heat, never reached equilibrium, never had any opportunity to agree on a temperature, and yet they match perfectly. It is like finding 2 cups of coffee on opposite ends of a continent, separated by thousands of miles, never having been near each other, and discovering they are both at exactly the same temperature. Not approximately, exactly. That kind of agreement without any opportunity for communication is not a coincidence. It is a signal. Something must explain it. In the early 1980s, a physicist named Alan Guth proposed an explanation. Suppose that in the universe's first fraction of a second, before the ordinary expansion we can trace and measure, there was a brief but ferocious burst of a completely different kind of expansion. Not the gentle, gradual drifting apart we see today, but an explosive, exponential stretching in which the universe doubled in size, then doubled again, at least 60 to 80 times over, all within a sliver of time so short it has no name in ordinary language. Everything we now see, the entire observable universe stretching across 93 billion light-years, was before this burst packed into a region small enough that it could easily reach a single uniform temperature, the way a small room comes naturally to one temperature. Then, inflation took that tiny, settled, uniform region and stretched it to cosmic size, smoothing it out, flinging its uniform warmth across the entire sky. The puzzle of the matching temperatures dissolves. The smoothness of the oldest light is not a coincidence. It is the stretched imprint of a region that was once small enough to agree with itself. Inflation works. Its predictions about the fine details of the oldest light have been tested against the data repeatedly, and they match with remarkable precision. It is not a fringe idea. For many cosmologists, it is the leading account of the universe's first instant, as close to established as anything in this corner of physics gets. And that success is exactly what makes its side effects so difficult to set aside. When you look closely at how inflation actually behaves, in nearly every version physicists have written down, you find that it does not switch off cleanly everywhere at once. The field that drives the expansion is subject to tiny random quantum fluctuations, small jitters, and those jitters mean that inflation ends in some regions before others. In a given patch of space, the field settles, inflation stops, and a hot expanding universe like ours forms from the released energy. But in the space surrounding that patch, the field hasn't settled yet, and that surrounding space keeps inflating, keeps doubling, faster than any new patches can form within it. Sit with the consequence of that slowly, because it is genuinely strange. The regions where inflation has ended are like bubbles in a boiling liquid, each one a separate universe, forming when the inflation field settles in that location, expanding and cooling into its own history. Our universe is one such bubble, a place where the furious stretching stopped and ordinary cosmic history began. But the space between and around the bubbles is still inflating, still doubling exponentially. And because that inflating space grows so much faster than the bubbles forming within it, it never gets used up. It never thins out. New bubbles keep forming inside it, each one a separate universe, possibly with its own particular physical properties, its own constants, its own ways of being, all of them embedded in the same endlessly inflating background ocean, never able to contact each other, separated not by distance but by an ever-expanding expanse of space that grows faster than any signal could ever cross it. This is called eternal inflation, and the picture it paints has a name you have almost certainly heard, usually delivered with more drama than it deserves. The multiverse, not as a science fiction flourish, clones, not as a metaphor, as what appears to be the direct mathematical consequence of the same inflation that so successfully explains the smoothness of the oldest light. Alan Guth himself has said it plainly. If inflation is correct, the multiverse is almost certainly real. The two do not separate easily. You do not get one without the other, Club, any more than you get a fire without heat. Now bring this back to the question that has guided every step of tonight's walk. If our universe is one bubble in an eternally inflating ocean, what was here before our Big Bang? The answer this picture gives is direct and quietly overwhelming. Before our Big Bang, the inflating background already existed. It was already expanding. Other bubbles may have already formed within it. The process was already running. Before that, the same. Before that, the same again. In this picture, the inflating background does not need a beginning the way our bubble does. It was simply there, already doing what it does, already producing universes the way a restless sea produces waves, without any particular first wave, without any moment at which the sea itself began. What we call the beginning of the universe was a beginning only for us, only for our bubble, a local event, a single flame igniting in an ocean of fire that had no first spark. Our sun, our galaxy, every structure we have ever mapped and named and wondered at, sits inside a single bubble among what may be an uncountable number of others, embedded in a process that by its own mathematics never needed to start, because it was never not running. It is a dizzying picture, and it would be easy to rest here, to accept the comfort of a universe that simply always was and always will be, a question that dissolves into its own answer. But that comfort, as we are about to see, is not quite as solid as it feels, because even this framework, the one most cleverly built to escape the problem of a beginning, turns out to be hiding something in its past. Something its own mathematics quietly insists is there. There is a particular kind of intellectual courage that doesn't get talked about enough in science. It is the courage to look at your own most beautiful idea and ask, seriously and without flinching, where it fails. In 2003, 3 physicists sat down and did exactly that to eternal inflation. Their names were Arvind Borde, Alan Guth, and Alexander Vilenkin. And the result they produced is one of the most quietly important theorems in modern cosmology, because one of its authors is the same Alan Guth who invented inflation in the first place. Their theorem can be stated simply, even though the mathematics behind it is anything but simple. Any universe that is on average expanding cannot be extended infinitely far into the past. If you trace the history of an expanding universe backward, the expansion itself forces you to reach a boundary, a point beyond which the history cannot be continued. You run out of past. Let that sit for a moment, because it matters enormously. The entire appeal of eternal inflation, as an answer to what came before the Big Bang, was that it seemed to dissolve the question entirely. The inflating background was always there, always running, no first moment required, no beginning to explain. The question of what came before simply evaporated, because there was always a before, stretching back without end. The Borde-Guth-Vilenkin theorem says that evaporation is an illusion. Even the inflating ocean has a shore somewhere in its past, the expansion that makes eternal inflation eternal in the forward direction, always producing new bubbles, always generating new universes. It is the very same expansion that prevents it from being eternal in the backward direction. Trace the history of the inflating background far enough into the past, and you don't find more of the same. You find a boundary, something that the mathematics cannot push through. The universe that seemed to need no beginning still needs a beginning. It is just a beginning that eternal inflation alone cannot describe. Notice who proved this. Alan Guth did not stumble into this result reluctantly. He helped construct it carefully, following the logic wherever it led, even when it led to a limit on the very framework he had spent decades building. That is what honest science looks like from the inside. Not defending your ideas past the point the evidence supports, but following the mathematics even when it complicates your own creation. The theorem does not destroy eternal inflation. The framework remains one of the most successful and most studied ideas in cosmology. What the theorem does is prevent it from being the final answer. It closes the exit that eternal inflations seem to offer from the problem of a beginning. The exit turns out to lead to another door, and behind that door the question is waiting, unchanged. Something still has to account for the boundary. Something still has to explain what was at the shore of the inflating ocean. The second crack in the eternal inflation picture comes from a different direction entirely, and it is in some ways more serious, because it is not about whether the picture is correct. It is about whether the picture is even science. The challenge comes from Paul Steinhardt, one of the original architects of inflationary cosmology, physicist, who helped build the very theory he now turns a hard eye toward. His concern is this: eternal inflation, by generating an infinite number of bubble universes, each possibly with its own physical properties and constants, becomes capable of producing any conceivable outcome somewhere in its endless expanse. Whatever you observe in your own universe, the theory can accommodate it. Whatever measurement you make, whatever constant you find, the theory shrugs and says, of course, there is a bubble with exactly that, and a bubble with the opposite, and infinitely many of each. A theory that can absorb any observation, that can never be contradicted by any measurement, has stopped making predictions in any meaningful sense. The thing that makes an idea scientific is precisely that it could in principle be proven wrong. A theory that is equally comfortable with every possible result has quietly stepped outside that boundary. It explains everything, which means, in a precise and important sense, it explains nothing in particular. This is not a complaint from outside the field. Indeed, it is a physicist who helped build the cathedral, looking carefully at the foundation and asking whether one of the load-bearing walls is actually holding anything up. These two cracks do not collapse the eternal inflation picture. Many serious physicists still hold to it and have considered responses to offer. What they do is keep the conversation honest. They remind us that the most elegant-seeming exit from the problem of a beginning is neither as clean nor as final as it first appeared, and they clear the way for the fourth framework, the one that takes the most radical position of all, the one that says the Big Bang was not a creation, not a bounce, not a bubble forming in a pre-existing ocean, the one that says it was a collision. Two entire worlds, drifting toward each other through a dimension we cannot see, finally meeting in a single instant of fire that became everything we have ever known. The fourth picture of what came before begins with a sentence that sounds like it belongs in a science fiction novel, and turns out to be careful, peer-reviewed physics published in serious journals by serious people with long records of serious work. What we call the Big Bang was not a creation, it was a collision. Two enormous objects, each one an entire world, drifted toward each other through a dimension we cannot see, cannot point to, and cannot walk along. They drifted for an almost incomprehensible span of time, drawn together by the faintest possible pull, and then they met, everywhere at once. And the energy of that meeting became everything we have ever known. To take that seriously, you need to know something about what one of our most developed attempts at a complete theory of physics actually says about the shape of reality. In ordinary experience, space has three dimensions: left and right, forward and back, up and down. Every movement you have ever made, every distance you have ever traveled, can be described as some combination of those three directions. But string theory, one of the most mathematically developed attempts to unite all the forces of nature into a single framework, requires more dimensions than that. In its most studied forms, reality has several more spatial dimensions than the three we move through, with the extra ones curled up so tightly, that scales so far below anything we could ever probe, that we never notice them in daily life. They are there in the mathematics woven into the structure of space itself, hidden only because they are wound up at scales that make an atomic nucleus look enormous by comparison. And in that richer space, objects can exist that we would never picture from inside our three dimensions. They are called branes, a word shortened from membranes. The The simplest way to imagine one is as a sheet, a surface extending through some number of dimensions, the way a flat piece of paper extends through two. Our entire observable universe in this picture. Everything you can see and touch and measure. Every galaxy, every star, every atom in the air in this room. All of it sits on one such brain, a three-dimensional surface floating within a higher dimensional space. We are not inside the universe, the way water is inside a glass. We are on it, the way ink is on a page, confined entirely to our own surface, unable to move in the direction that would take us off it. Picture a thin film suspended in a larger medium. Everything we know lives on the film. The extra dimension runs perpendicular to it in a direction we cannot face. Now here is the setup that leads to the collision. There is another brain lying near ours in that extra dimension. A second sheet, parallel to our own, separated from us by a gap that is tiny by the standards of the cosmos, and yet completely beyond our reach, because we cannot move in the direction that would take us across it. That second brain has mass. So does ours, and gravity, alone among all the forces, is thought to leak across the gap between brains the other forces. Electromagnetism, the strong and weak nuclear forces, are confined entirely to their own brain, bottled up within their own surface. But gravity bleeds through. This detail is worth pausing on, because it quietly explains something that has puzzled physicists for a long time. Of all the forces of nature, gravity is by far the weakest. Not slightly weaker, absurdly, almost comically weaker. A small magnet can lift a paperclip against the gravitational pull of the entire planet beneath it. The whole mass of the Earth is losing a tug-of-war to an object you could hold between two fingers. Why is gravity so feeble compared to everything else? In this picture, there is an answer. The other forces are stuck on our brain, their full strength confined to our surface. But gravity is not confined. It spreads into the extra dimension, leaking away from our brain into the space around it. What reaches us is only the thin remainder left, after most of it has spilled somewhere we cannot follow. Gravity feels weak not because it is weak, but because most of it is somewhere we cannot go. And it is exactly that leakage, that quiet bleeding of gravity across the gap, that pulls the two brains toward each other. Slowly, almost imperceptibly, across what may be an enormous span of time, they fall together through the unseeable dimension, drawn by the very force whose weakness has puzzled physicists for generations. Let yourself sit in that approach for a moment, because it is one of the strangest scenes physics has ever offered. Picture our universe not as the inside of an explosion, but as a calm, enormous sheet drifting in a darkness that has a direction we cannot face. Somewhere just beside us, separated by a gap we cannot measure and cannot cross, another whole world drifts in parallel. A second sheet as vast as our own. Nothing passes between them. No light, no matter, no signal of any kind. Only gravity reaches across the gap, the faintest possible thread of attraction, drawing the two surfaces toward each other over ages so long that the entire current history of our universe would be a single frame in the film. For almost all of that time, nothing seems to happen. The two worlds simply drift closer, silent, patient, cold, and then they touch. Not at one point, not at one location, everywhere at once. The entire surface of our world meeting the entire surface of the other in a single instant, like two vast sheets of glass, finally coming together across their whole area simultaneously. And in that instant, the energy of the collision floods into our brain everywhere at once, igniting it into a hot, dense, expanding fire. From the inside, on our brain, that release would look exactly like a universe erupting from a single hot beginning. It would look like the Big Bang, because it was the Big Bang. Not a creation from nothing, a collision between two pre-existing worlds. This idea is called the ekpyrotic scenario, from the ancient Greek word for a great fire, a conflagration. It was developed around 2001 by Paul Steinhardt, the same physicist we met in the last part questioning eternal inflation. They're working alongside Neil Turok. Both had spent years on inflation and had come to believe it carried unresolved problems deep in its foundations. The ekpyrotic model was their alternative, built from different mathematics, resting on different assumptions, and leading to a fundamentally different picture of what the Big Bang actually was. In the fuller cyclic version of this idea, the collision is not a one-time event. After the brains meet, they rebound, drifting apart again through the extra dimension. Over another immense span of time, gravity draws them back together. Another collision, another Big Bang, another universe igniting from the meeting of two ancient worlds. Each separation is a long expansion. Each approach is a slow, patient fall through the dark. Each collision is a new beginning. The universe in this picture has no single origin. It has a rhythm, a slow, vast heartbeat, worlds meeting and parting across the unseeable dimension, perhaps without end, perhaps without beginning. And crucially, the ekpyrotic model is not merely a beautiful story. It makes a specific prediction that differs from what inflation predicts. Both mechanisms would have produced a background of gravitational waves in the first instant, but the character of those waves would be different in each case. Inflation predicts a background with a particular shape across different wavelengths, carrying a slight characteristic tilt. The ekpyrotic collision predicts a much flatter spectrum, with that tilt essentially absent. Two different signatures, in principle distinguishable, waiting in the gravitational wave background. For an instrument sensitive enough to read them, the test has not yet been run. The instruments needed to run it are still being built, but the prediction is on the table. Clear, specific, falsifiable, a minority position in the field, but a patient one, holding its breath in the literature, waiting for the data to catch up. We have now walked through 4 separate frameworks, 4 different pictures of what existed before the Big Bang, each built by serious people, and each resting on real mathematics, each pointing at a genuine something on the other side of the wall, where general relativity fell apart. But there is one more thing we need to sit with before the end of this walk. Something quieter than any of the 4 frameworks. Something that doesn't give you a before at all. Not because there was nothing there, but because the word before may not mean what we have been assuming it means this entire time. Every step of tonight's walk has rested on a single quiet assumption. An assumption so basic we never pause to examine it. We have assumed that time is real, that before and after are genuine directions, that the universe has a history, the way a story has a sequence. One thing leading to another in a chain that stretches backward through the bounce, through the previous aeon, through the inflating ocean, through the collision of ancient worlds. Every framework we have explored needed time to be solid ground. Now we have to face the possibility that the ground is softer than it looks. In the 1960s, 2 physicists named Bryce DeWitt and John Wheeler attempted something extraordinarily ambitious. They tried to write down the single most fundamental equation for the quantum state of the entire universe. Not the quantum state of a particle, or an atom, or even a galaxy. The universe itself, everything at once. The most complete possible description of reality, combining quantum mechanics with gravity at the largest conceivable scale. They succeeded in producing something. An equation that physicists still study and work with today. But the equation has a feature so peculiar that when you first encounter it, you assume you have misunderstood. The Wheeler-DeWitt equation, the candidate for the deepest description of reality we have ever written down, contains no time, not a hidden time, not an approximate time, no time variable at all. The symbol for time, which appears in virtually every other equation in physics, simply is not present. It was not left out by accident. It is not waiting to be added. When you combine quantum mechanics with gravity at the most fundamental level, time, as a variable in the equations, disappears. Sit with how strange that is. Every equation you have ever encountered, even informally, assumes time is there. Things move over time. Energy changes over time. Particles interact at particular moments. The entire structure of physics, from a stone falling to a planet orbiting, built on the assumption that time flows, that there is a before and an after, a past and a future, a background against which everything happens. And then you write down the equation for everything at once, the most fundamental description possible, and time quietly vanishes from the page. Physicists call the puzzle this creates the problem of time. And it is exactly as serious as it sounds. The most arresting interpretation, the one that should make you go very still, is that time is not fundamental, that at the deepest level of reality, time as we experience it, as a flow, a passage, a difference between what was and what is, does not exist in the underlying structure of things. What we live as time would then be something that emerges, the way temperature emerges from the motion of particles. Case, single molecule has no temperature. Temperature only appears when you have enormous numbers of molecules moving and colliding together. It is real and measurable and can burn you. But it is not a property of the bedrock. It lives at a higher level of description, emerging from something underneath that has no temperature at all. Time, in this view, may work the same way, real at our level, undeniable in our experience, and yet not part of the most basic layer of reality, emerging from an underlying structure where it simply is not present. Now bring this back carefully to everything we have built tonight, every framework we explored, the bounce, the previous aeon, the eternal ocean, the collision. Every one of them uses time as its scaffolding. They all describe a sequence. First, there was a contraction, then a bounce. First a previous universe, then ours. First an inflating background, then a bubble. They all lean on before and after as if those words are solid ground. But if time itself is emergent, if it is not part of the most fundamental layer of reality, then the question what came before the Big Bang may not be a question with a hidden answer waiting to be found. It may be a question that quietly falls apart at its own foundation, not because the answer is unreachable, but because the question itself was built on a floor that may not be there. Stephen Hawking offered a comparison for this that has stayed in the literature because it captures the strangeness so exactly. Asking what came before the Big Bang, he suggested, might be like asking what lies north of the North Pole. The question sounds perfectly grammatical. North is a real direction. You can travel north for a very long way, but when you reach the pole, north simply runs out. Not because something is blocking you, because the concept itself stops applying at that point. Every direction from the pole is south. There is no further north. Not a wall, not a door. Just a place where the direction you were traveling ceases to be a direction. If time emerged with our universe, then before may be a direction that runs out as you approach the beginning. A word that means something real from where we stand, and nothing at all from where the question points. I will not tell you this is settled, it is not. The fact that the Wheeler-DeWitt equation contains no time is genuine, and it is telling us something real. But whether it means time is fully emergent, or only that our description needs fundamental repair, is something the field has not resolved. What it means for tonight is this. Every answer we found carries this shadow alongside it. Each bounce and aeon and bubble and collision was built using time as its foundation. And the most fundamental equation we possess is quietly suggesting that the foundation may be something we built ourselves. Something that belongs to us rather than to the universe. Story. Our time-bound minds cannot help but tell. Perhaps the most honest thing that can be said about the question what came before is not any of the four answers we walked through tonight. Perhaps it is something stranger and more humbling than any of them. Perhaps before is the most human word in the universe. For most of human history, everything we have talked about tonight would have ended exactly where the last part ended. With a question, with a wall, gone, with the honest admission that we do not know, cannot see, and may never reach the place where the answer lives. What is different now? Tav. What makes this our moment rather than simply a retelling of an ancient question? Is that for the first time in the history of any civilization that has ever looked up at this sky, we are building the instruments to listen past the wall, not to see past it. Seeing is finished at 380,000 years, and nothing we build will change that. But listening is a different matter, and the messengers we are learning to listen for, gravitational waves, carry information from places and times that light can never reach. The first machine worth knowing about is already approved, already funded, and already being built. It is called LISA, the Laser Interferometer Space Antenna, and it will do something no gravitational wave observatory has ever done before. It will leave the Earth entirely. LISA will consist of 3 spacecraft arranged in an enormous equilateral triangle, each side of it approximately 2.5 million kilometers long, trailing the Earth in its orbit around the Sun. Out there, free from the trembling of the ground, free from the rumble of traffic and weather, and the quiet geological shifting of the continents that limits what any ground-based detector can feel. The 3 spacecraft will bounce laser beams between themselves and measure with extraordinary precision any change in the distance between them. A passing gravitational wave stretches and squeezes space itself, and Lisa will feel that stretching at a sensitivity no instrument sitting on the surface of a planet could ever achieve. The European Space Agency formally approved the mission in 2024. Its prime contractor was selected in 2025. It is planned to launch in the 2030s, and when it is operational, it will open a window onto gravitational wave frequencies that are simply invisible to anything we have built so far, including, potentially, the faint primordial background left over from the first fraction of a second of the universe's existence. The background that carries, encoded in the geometry of space, the imprint of whichever of our four frameworks was actually operating. At the moment everything began, on the ground, next-generation observatory, called the Einstein Telescope, is in development in Europe. It will be built underground, in the shape of an equilateral triangle with sides 10 kilometers long, shielded from the surface vibrations that limit current detectors. It is designed to be sensitive enough to detect gravitational waves from events across a much larger fraction of the observable universe than current instruments can reach, and to hear signals at frequencies and from sources that remain beyond the reach of anything operating today. Site selection and detailed planning are underway, with construction aiming to begin within the next decade. The oldest light still has more to tell us as well. An array of telescopes high in the dry mountains of northern Chile, called the Simons Observatory, is already operating and gathering data, studying the cosmic microwave background at a level of precision the earlier satellite missions could not reach. It is searching specifically for the faint polarization signal that inflation would have imprinted in that ancient light, a swirling pattern in how the light is oriented that the violence of the inflationary expansion should have left behind, and that the ekpyrotic collision predicts at a level too small to see. Finding that signal or not finding it will not prove or disprove any of our four frameworks on its own, but it will meaningfully narrow the field. Each of these instruments is a machine for reading the ash. After a building burns to the ground, you cannot see the building anymore, but the chemistry of what happened is written in the residue pattern of the char. The traces left in the ground. The fire does not erase the past. It transforms it into a record that a careful investigator can still read. Whatever existed before our beginning, whatever bounced or aged or inflated or collided, did not vanish without a trace. It left a residue encoded in the curvature of space, in the faint patterns of the oldest light, and above all in the background of gravitational waves that even now are crossing the universe, passing through this room, passing through you, carrying news from before the oldest light was ever set free. We cannot see the building that stood before, but the ash is real. And for the first time, we are learning to read it. We began tonight with a question we were never supposed to ask. What was here before the beginning? We have walked a long way since then, through a broken equation that confessed it could not see what it was pointing at, through a wall of ancient light that marks the oldest thing any instrument will ever show us, through four separate frameworks, each built by serious people using real mathematics, each arriving at the same fundamental answer: not nothing, something. Something with structure, with physics, with a history of its own that preceded every particle you are made of. Something was here before us, maybe it was a previous universe, contracting toward a floor woven into the grain of space itself, hitting that floor and bouncing outward into the expansion we are still riding tonight. Maybe it was a complete cosmos that lived its own long life, built its own stars, watched them die, and at its own infinite exhausted end became our blazing beginning. Maybe it was an eternal restless ocean inflation, already producing universes the way a sea produces waves, with no first wave and no moment at which the sea itself began. Maybe it was two ancient worlds, drifting toward each other through a dimension we cannot face, finally meeting in a collision whose fire became everything we have ever known. We do not know which of those is true. We may not know in our lifetimes. We may not know for generations, and underneath all of them sits that quieter, stranger possibility, that before is a word that belongs to us and not to the universe. That time is something we bring to the question, rather than something the question contains. But here is what we do know, and what is worth carrying with you as you drift towards sleep. The question is no longer sealed. The room that seemed to have no door turned out to have one. The equation that broke at the beginning was not closing something off. It was pointing at something it could not describe, which is a completely different thing. And the instruments we are now building, the machines floating in space and buried underground and perched on cold, dry mountains, are aimed at exactly the place the question lives, beyond, listening for the faint remnant signal of whatever was operating before the oldest light was set free. Somewhere out there in the dark, right now, gravitational waves are crossing the universe. They are passing through the walls of this room, through the air around you, through you, Dov, arriving from distances and times that no telescope will ever photograph, carrying the imprint of physics from before the beginning, from behind the wall, from whatever ancient thing was here before our fire was lit. They are not waiting for us to be ready. They have been crossing the universe for longer than our planet has existed. They will keep crossing it. Long after every instrument we have ever built has gone quiet. We just have to learn to listen, sleep well,